So here are the answers for our homework assignment. Again, this is linked on Canvas that you can see now. I don't want to go through everything right now, but I did want to give you the opportunity, if anything stood out as something that you'd like to discuss or go over, we can do that. Did anything jump out? Yes?
Can you go over the difference between the variability and like range?
Yes. So the question is about the difference between variability and range, which we'll look at a little bit more today. Range is defined as max minus min. So variability is more of a general term in the sense of how does the set vary? Do you have a lot of the data compact all around the center, or is it very spread out? Okay, so does it vary as part of variability? While range, you're still going across the entire span, but it's specifically max minus min. Okay? That's a good question. Anything else? Anybody at home? And if something does come up as you look at the answers a little bit closer, you're welcome to ask me. Yeah, Gabby?
I'm confused on this fact. How do you make a histogram when you have like the table of information?
So you have that frequency table created. So the histogram, so like on this last question here, this is 35, I think. The frequency table has the intervals listed out, and then in the column next to it, you have the frequency or the quantities of each. So that quantity is dictating the height of the bar for each histogram. So in this case, they were looking at the nurses per state, and the frequency was measured in number of states that had that rate of nurses per 100,000 people. So 500 to 600 per 100,000 people. Looked like there were 3 states there, so that was the height of that bar. The next interval was 600 to 700. There were, looks like 5 states that fell into that range, so that's the height of that bar. Does that make sense?
Yes.
Okay. Anything else? Okay, so I'll start to look through those homework assignments, and should get credit for those this week. Today we're moving on into our second section, which is descriptive statistics. It's looking at the measured calculations for describing a data set. And a little bit of a joke to start out here. It says a statistician can have his head in an oven and his feet in ice, and he will say that on the average he feels fine. Okay? Giving you that idea that the average doesn't necessarily mean what's typical or what's actually going on. Okay? Sometimes we like to overly condense things down and to say the average this or the average that. Well, average gives you no idea about the variation or the spread that's going on within that data set. Okay? Now this is an extreme and a joke right here. Okay? Burning up and freezing cold averages out to feeling fine. Okay? But there's more to it than just that. I have 2 little warm-up discussion questions to take a look at here today. First one says, if you were to read the results of a study showing that daily use of a certain exercise machine resulted in an average 10-pound weight loss, what more would you want to know about the numbers in addition to the average? And you're given a little hint there. Do you think everyone who used the machine lost 10 pounds? So let's say that you're interested in buying this piece of exercise equipment, and maybe you're interested in losing like 10 pounds or something like that. So you really want to know, like, this advertised claim that on average you're losing 10 pounds, like, what's going on with that? Yeah? Any thoughts about this? What more would you want to know? Anybody at home? Well, we talked a little bit last week about the people in the sample. Okay? And we talked about the sample size. Okay? So let's start with that. With sample size, you're talking about this group averaged a 10-pound weight loss. Well, the degree to which you believe in these results might differ. If it's only a group of 5 people, right, you don't know much about that group of 5 people, and a lot of things can happen over such a small sample. As opposed to if this was a group of 500 people and they all averaged a 10-pound weight loss, those results might be a little bit more legitimate, okay, because it's past the test of time. It's occurred across a large enough group of people, as opposed to a sample size of 5. Okay? I gave you the extreme case of what if I went home and played the lottery last week. Okay? Yeah, we know what's going to happen in the big picture, but across a small sample, okay, a one-time chance of playing the lottery, it's still unlikely, but it does happen. It could happen. Okay? You could get 5 athletes in this, okay, that it's very easy for them to work out. They have a 10-pound weight loss. Okay? Or maybe on the reverse. Maybe you have people who are overweight and have 10 pounds or more to lose, so that happens rather quickly. Okay? You don't know anything about those people. Also, if you're talking about the average, we come from this idea that average means what's typical or what's common. And that's not always true. Okay? What's average is the mean. And we know how the mean is calculated. Add all the terms up, divide by the number that you have. So again, let's pretend that we're talking about that sample size of 5 people, although I know that's an extreme low. We could have this group of 5 people, lost 10 pounds, lost 10 pounds, lost 10 pounds, lost 10 pounds, lost 10 pounds. That gives you an average of 10-pound weight loss. Or maybe the first person loses 10, another person loses 20, but a different person loses 0 pounds, another person loses 30 pounds, and another person gains 10 pounds. That averages out to a 10-pound weight loss as well. Okay? I think a sample like that would maybe not really bode too nicely for the results of that exercise equipment. If somebody's gaining 10 pounds, I mean, yeah, somebody else lost 30 pounds, but there's something going on that it's probably not the exercise equipment alone that's contributing to the change in that response variable, the weight loss. Okay? Let alone, we have no idea about any other variables going on here. In addition to exercise, okay, the other thing that rather frequently accompanies exercise in terms of weight loss is diet. We've got no idea about the diet of these people. Okay, so diet and exercise go hand in hand with one another. I think that you'd like to know a little bit more information about this scenario before you wholeheartedly say, that's the way I'm going to lose 10 pounds, take my money, here it is. Okay, you have to kind of look a little bit deeper into what goes into that average. One other warm-up scenario here. It says a real estate website reported that the median price of single-family homes sold in the past 9 months in the local area was $136,900, and the average price was $161,000 some dollars. How do you think these values are computed, and which do you think is more useful to someone considering purchasing a home in this neighborhood, the median or the average? We talked a little bit about average or mean already. I know you've heard of median before. What is median and how is it calculated? What?
It's the one in the middle of all the values.
Yes, median we think middle. So to find the median, if you were to find it by hand, which honestly we will not do, okay, we'll let some piece of technology take care of that for us, but line them all up in order, okay, smallest to largest, and find that middle number. So sometimes people like to think of it as like canceling terms out, okay? Take the highest one, take the lowest one, they cancel each other out, and keep doing that until you get to that middle number. Now, with that in mind, okay, look at these. Look how much these numbers differ. The median, that middle number, is about $137,000. The average, the mean, is about $161,000. So these two values, these two measures of center, differ by about $25,000. Why is there that difference between these two measures that are supposed to give us something kind of similar? Okay, Emily?
There could have been an outlier on the higher side. There could have been a house for like $500,000 that would have brought up the average.
Exactly, yeah. You have an outlier here. And in this case, in this housing scenario, an upper outlier makes sense. Okay? You could have a house that is way above the value of the others, bringing up the mean home price in that neighborhood. I always think of an example a few years ago when LeBron James was playing for the Cleveland Cavaliers. You know, he's from Ohio and he was like the hometown athlete. Well, he built a $40 million mansion outside of Akron, Ohio, and he commuted into Cleveland for his games. Now, how many other $40 million mansions do you think are in Akron, Ohio? Not many. So that mansion is going to be an outlier that brings up the mean home price in that area. However, the median is unaffected because the way you calculate median, remember, everything's listed out in order, that $40 million mansion is quickly negated by whatever the lowest price shack in the neighborhood might be. And then you continue to work your way to the middle. So it doesn't matter that that was a $40 million house. It could have been whatever the next highest value is, and the median is still going to be the same. Okay? So, big picture here. Median is resistant to outliers, but the mean is influenced by outliers. It's pulled in the direction of a possible outlier. So we're going to be looking at these measures of central tendency, mean and median. We'll briefly talk about the mode for a minute. 5-number summary as a way of looking at the picture, the spread of the data set. We have one more display called a box plot to take a look at. And lastly, we'll be looking at calculating and interpreting measures of variability and relating them to the measures of center. That's what I just said. I need to delete those slides. Okay, so let's talk a little bit about the mean. Okay, the mean, or the average, is calculated. It's the arithmetic average. Okay, and you know how to calculate it. You add all of the terms in that set and divide by the number of items that you have. Okay, so the symbol that we have to represent mean is this symbol right here. X with a little line on top of it, we call it X bar. Now, really, we have two symbols that represent mean. X bar is one of them. That represents a sample mean. Okay, so if we're working with a sample, X bar represents the mean of that sample. If we're talking about the entire population, then we're going to use this Greek letter mu, spelled M-U, and it looks kind of like a U with a little bit more of a distinct tail on the end. This is a population mean. Now, for right now, most of our work will be with X bar. And as we start talking about how the sample is a representation of the population, we'll start to bring in mu a little bit more. But for right now, we're just using X bar. Couple of formulas for calculating the mean, okay? Adding up all of the individual x's, the elements of the data set, and divide by n the number that you have. Or if you wanted to use sigma notation here, the sum of all the x's multiplied by 1 over n gives you that x bar. Again, don't really worry about calculating this by hand. We're going to start to look at how technology can assist that, starting with the graphing calculator today. Now, with the median, we said that mean cannot resist the influence of extreme observations. That $40 million mansion pulls the mean in that direction. Okay? It's not a resistant measure of center. Median is. Because median is the middle, okay, we represent it with capital M, just like we did midpoint way back in geometry. M is the midpoint of a distribution, the median. Okay? Half of the observations are going to be smaller than the median. Half of the observations are going to be larger than the median. Now, in the case where you would have an even number of elements in the data set, you're going to have two middle numbers. To get the median there, you find the mean of those two middle numbers. So in that case, it's possible to have a median that is not an element of the original data set. Okay. Any questions up to this point? Okay. Now, here's a quick example problem. We have a data table that represents the commuting time in minutes of 5 randomly selected North Carolina workers. So 15 people in North Carolina were surveyed about their average commute time to work. And we see 5-minute commute for that person is pretty easy. Looks like the biggest here is 60 minutes. So to find the mean, add them all up, divide by the 15 that we have, the average commute time is 22.5 minutes. Now, to look at the median, a good way to organize these data values would be to make a stem plot. And right away we can see that most of our data is on the lower end. And our maximum value of 60 minutes, it stands out quite a bit. Okay? Nobody was in the 50s, and the two values that we had in the 40s were 40 itself. Okay? So this is like a third of the spread above the next highest value. So that 60-minute commute time is a possible outlier. And when we calculate the median, it's 20 minutes. So we see that the mean, 22.5, has been pulled in that upward direction because of that possible outlier, that 60-minute commute time. Now, comparing the two, the mean and the median, they both measure the center. And they're both useful. Okay, I don't want you to think that because this mean is susceptible to outliers that it's like a worthless measure and we should abandon mean and always go with median. No. Okay? The mean and the median are actually going to be the same measure if you have a perfectly symmetric data set. So when we start talking about the standard normal curve, the bell curve, and remember what that looks like. It's symmetric right there. In the middle, it is the median value, okay? Because median means middle. But because it's perfectly balanced, you know how you calculate the average. You have the same thing on the left going with the same thing on the right. The mean is also perfectly in the center as well. Additionally, I told you we're going to talk about mode just a little bit. Remember, the height of this curve is the most commonly occurring item. And the peak of that curve is right at the middle, So the mode is also occurring right at the center of that standard normal bell curve. Okay, so when we look at this curve closer in our next unit, a whole lot of stuff is happening when you have a symmetric data set. But if the set is skewed, the mean is pulled in that direction. Okay, the median stays in the middle, but if you had a data set that was skewed to the right, median's going to stay around here somewhere, while the mean is pulled over somewhere in this direction, towards the direction of the skew. Let's look at an example together here. I have a set of numbers, and if you have a graphing calculator, this would be a good time to take it out. Remember, we do have that emulator that's on Canvas I've linked to. The way that works is you're going to go to the website and download that ROM file from Canvas, and then once you're at that website, you can identify where that has been downloaded to and upload it, and it should work. Maybe you don't want to do that now. That's okay. I'm going to be bringing my calculator up here. Now in class, I do have two calculators. If you would like to borrow, or you feel comfortable borrowing, they've been wiped down with the sanitizing wipe. If you want to borrow one right now, you're welcome to. If you'd like to just kind of watch, that's fine by me as well. I'm going to change screens here, so if you're typing these data values in on your own, it'll be up on a different screen. Let me log in on my other account here. This one I need to join and very good. Okay. So we have our calculator right here. Now, the way this works, our stat button is located right here around the center of the calculator. And when we click that, it brings up our edit menu, and that's where we enter the values in. I'm sure that you've used this before in previous classes, whether that's a math class or science class or something like that. And we're typing all of those numbers that represent test scores into list 1 on the calculator. Most of the mistakes that are made with calculations like this are because of data entry, which is the biggest drawback of this graphing calculator. Like, this calculator is a 35-year-old piece of technology. All right, it's older than all of you. Okay. What is very cumbersome about this is that it's not easy to enter data. It's not easy to transfer data. Okay. It's become outdated, but it's kind of so ingrained into the American mathematics classroom that it's still here. All right, and it's really like the only piece of technology that's allowed for a lot of the tests that you take. Okay, I'm not saying tests in my class. This year I'm going to try to be more creative and expand and allow you to use some of the other tools that I'm talking about later this week. But like that CHS exam, unless they make changes or something for this year, the graphing calculator is the only technology that you can use. So we still need to talk about it a little bit, but it has its major drawbacks. Now, once we have our data entered into the list, we're going back to our main screen, and when we press the stat button, Couple observations here. Sort A and sort D. That's to sort that list in ascending order or descending order. That would be helpful if we are finding the median by hand, okay? But we're not going to do that. That would be helpful if we are going to make a stem plot, because we need those sorted out in ascending order. The calculator does not make a stem plot. Wednesday, GeoGebra will make a stem plot pretty easily for us. Okay, so that's one of the benefits. But if we were making one by hand, then we'd have to use the calculator to sort the list for us. For right now, we're going over to the middle menu, which is Calculate. And our very first option is the one var stats, one variable statistics. Okay? We'll choose that, and some of the newer calculators look like this, where you identify which list to refer to your data set. The default is list 1, that's good. Older calculators just say one var stats and have open parentheses. Either way, just hit enter. And here are our important numbers. So very first value at the top, X bar, is our mean, 76.04 if you round that. And so we have about a 76 as the average test score in this class. The next two values aren't really important. Sigma x is the sum of all of the values in our list, and sigma squared x is the sum of all of the squares of the values. Neither is really important to us here, so just ignore those. The next two values, sx, and that's the Greek lowercase letter sigma. Sigma x, those both represent standard deviation. This is what you will use to find standard deviation. Later in class, we'll talk about the manual calculation of standard deviation, not because I want you to do it by hand, but because it gives us a little bit of an idea about what it is and where it comes from. But standard deviation, okay, Sx represents the sample standard deviation, sigma x represents the population standard deviation. Okay. Just like we had with mean, we had two measures, two representations. I'll show you the difference in the calculation when we look at it by hand. For us, just use sample standard deviation. So Sx is good for us. Okay, they're always going to be approximately the same. They're both about 14 here. Continuing to scroll down, n is the number of items in our data set. We had 28 test scores. And then our last 5 numbers here. This is the 5-number summary. Min, Q1, median, Q3, and the max. We know what the min and the max are. We could use those to find the range. We know what the median is. So look at the median here of 78.5 and compare that back to our mean of about 76. Notice that the mean is lower than the median. What that means is we might have a lower outlier. The mean has been pulled down in that direction. So even if it's not an actual outlier, then we have some low values that are kind of standing out here. And with a min of 32, yeah, that is a pretty low test score. Q1 and Q3, those are the first and third quartiles. We'll talk about those in just a second. Okay? But anybody have any questions here about how to use those one var stats? Yeah? It's easier than doing it by hand, okay? And the technology, you're somewhat familiar with it. You've been using the calculator for years now. All right, let me go back to my other display here. Oh, infinite regression. Calculators are also good at being dropped on the floor too. Okay. Now, we talked about those quartiles. Yeah. We We said a measure of center alone can be misleading. We saw a couple warm-up problems where that's all we had presented to us. We'd like to know something about the spread. Okay. The quartiles give us a little bit of a picture about what that spread of the data set looks like. Okay. This goes on to say we could look at the largest and smallest values, and we will, but like the mean, they are obviously affected by extreme values. Okay. Max and min alone aren't great. Okay. We have a test score of, what was it, 32? Okay. Our next lowest test score isn't until 55. Okay, so it doesn't give us much of an idea about the other non-max and min values if we just look at the extremes. Okay? The quartiles split the data set into 4 quarters. We already know that the median is that middle set. So we've got 50% of our data set below the median, 50% of our data set above the median. Q1 is the first quartile. It's like the median of the first half. Okay? So from min to the median, you find the median of that. That is the first quartile. Okay? From the median to the max, you find the median of that set. That's the third quartile. The 5-number summary consists of min, Q1, median, Q3, max. This is a quick picture that gives us an idea of the entire spread of the data set. Okay? Knowing that we have a quarter here, a quarter there, a quarter there, a quarter there. Okay? It allows us to get an idea of what that distribution looks like. And a box plot is a visualization of that 5-number summary. Okay? So in general, a box plot, or you may have learned it as a box and whisker plot, the rectangle or the box represents Q1 on the left side, Q3 on the right side, and then you have a vertical bar somewhere inside that box representing the median. And then horizontal bars or whiskers extending out to the sides representing the min and the max. Now, you have quarters identified from this box. So, between the min and Q1, we have 25% of our data set there, 25 tucked in there between Q1 and the median, 25% between the median and Q3, and 25% extending all the way from Q3 to the max. Okay. Now, these are not equally sectioned out, and there's a reason for that. It gives us an idea of the spread. So when we have a very narrow margin right here between Q1 and the median, that's 25% of the data, just like every other section. However, it's very condensed, meaning we have a lot of values right in there in that small region. As opposed between Q3 and the max, 25% is spread out. There's a lot of variability in that upper quartile. Okay? So it gives us an idea about what the distribution looks like. Here's another example. Remember we talked about the North Carolina commute times? Here is New York City commute times. We have more of them in this case, but we have the 5-number summary identified for us. Min Q1, median Q3, and the max. So we can make a box plot to display this 5-number summary. So the middle box goes from Q1 to Q3. We also have an X scale providing some reference for us here with these values. That is a good thing to have. Our median value here is 22.5 minutes. That goes right there. And then this extends out to the min. Minimum here is 5-minute commute time, quick walk to work. And then the maximum commute time is 85 minutes. So again, a lot of variation there. Notice that our next highest value is 65 minutes. Okay, so there's a 20-minute difference between our max and our next highest value. There's a lot of variation there. That max might be an outlier. Any questions so far? Now, to identify if it actually is an outlier. Remember last week I said we have kind of two interpretations of that word. In a non-mathematical sense, an outlier is just a value that's away from everything else. But in a statistical sense, we have a precise definition of how far away is far enough to make it an outlier. Okay? We use a measure of spread called the interquartile range. So remember, range itself is max minus min. Interquartile range, or IQR, is Q3 minus Q1. So we use this 1.5 times the interquartile range rule to say that if we were to use Q3 and add on 1.5 times the interquartile range, anything above that is going to give us an upper outlier. Okay, so 1.5 times the interquartile range, add that region onto Q3. Anything that's beyond that is an upper outlier. Similarly, on the left end, Q1 minus 1.5 times the interquartile range. That gives us a lower outlier. So let's take a closer look at this here with our example problem. Q1 and Q3 were 15 and 42.5 minutes respectively. So the interquartile range, 27.5 minutes. Now, to get 1.5 times that value, work it out, gives us 41.25 minutes. So we go to those values here. Q1 being only 15. 15 minus that 41.25 takes us down to a negative 26.25. So that doesn't make any sense for outliers because we don't have any negative values. And we weren't expecting any low outliers in this example. Okay? Upper outliers, on the other hand, they might be a possibility. Q3, the value was 42.5. So you add another 41.25 to that, we get 83.75, which is just smaller than our max of 85. So that 85-minute commute time is a mathematical outlier in this problem. Yeah. Now, any questions on that before we get into standard deviation? Anybody at home? All right, a couple things. I want to show you how to do a box plot with the graphing calculator. So I'm going to switch screens again and go back to our other data set of test scores. Those of you in class, if you want to take a little bit of a mask break, you can. Again, we've said just kind of stay at your seat. You can remove the mask as long as you're staying behind your shield. No talking with the mask off. And then after 5 or 10 minutes or so, you can just raise it. And obviously, you can keep your mask on if you'd like. So let me go back to the calculator. Okay. So here's our calculator. We left off with our 5-number summary. Now, to have the calculator make a box plot for us, it's always good to check the y equals screen first. If you have any equations in there that you don't need, clear them out. If you need them for another class, put your cursor over the equal sign and hit enter so it kind of overlooks that equation, because we don't want them kind of distorting our view. So once that's set up, we're going to go to second and y equals for a stat plot. And our first plot, okay, hit enter. And we want to make sure that it's turned on, so we'll hit enter over the on sign there. We want to choose our type of plot here. The first two options are scatter plots. Third one that I'm currently on is a histogram. But we have two options for a box plot. You'll notice that one of them, the second one, has the whiskers extending all the way to the max and the min. This one right here has a couple of dots, meaning that if we have outliers, it will identify the outliers for us. This is a nice one to choose because we don't even need to use the equation. Okay? This one will identify outliers for us. So let's pick that by hitting enter. And if you were to just hit graph, you're probably either going to get like a blank screen like I have here, or you're going to get something that you might see part of the box plot but not the whole thing. Not a great representation. Whenever we're looking at a stat plot, a good place to start is with the zoom button right in the top middle and go down to number 9. Number 9 is zoom stat. This will automatically give us a good window based off of the numbers in the field, and I didn't change mine to the box plot. Go back and never hit enter. There we go. Now, there's my box plot after doing the zoom 9. And in this case, I can see box and whisker there. It looks like a little bit of a data point down there. I'd like to make some adjustments to my scale though. Okay. Now, my minimum is the minimum value that I have. I want to give myself a little bit more room there, so I'm going to make that minimum 30. I'll let the max go up to 110, although we know we cannot exceed 100% with the test score. The scale will be the step size. So I'm going to make this 10 so I can very easily see who scored in the 50s, who scored in the 60s, and the 70s, etc. Kind of like the step size we wanted when we were making our histograms. The y values don't matter too much. We could make our y min 0 or whatever, and we'll leave that scale alone. So now when we go back to graph, now it gives us a nice picture for the box plot, and we can clearly see that that low test score of 32, that's an outlier. So if we were to press the trace button, which is right next to graph, we can trace along these critical values. Okay? It starts out that 55 is our next lowest value that's not an outlier. Okay? It doesn't have a special representation here, but it's part of the rest of the set, and it's where the tail extends to. If we go to the left, there's our outlier of 32 in the min. Going to the right, here we start to see our 5-number summary, Q1, median, Q3, and the max right there. Questions with the box plot? Okay. It's kind of a lot of work to get it, but if you already are using the calculator for like the 5-number summary or the 1var stats, it's really just a few more buttons to press to get that box plot, that representation of it. Okay? While we're here, let's look at the histogram as well. Back on the stat plot, so second y equals. Going back here, now I'm just changing this back to the histogram. And I've already manipulated the window and the scale a little bit. So here I should be able to go just to the graph, and I can see that histogram pretty nicely. There's that outlier down below. Remember, the height of the bar is the frequency of those intervals. So if I press trace again, I can go along through each bar, and it will identify what the boundaries of that bar are. Okay, so 30 to 40, we had the one test score in that interval. And going to the right, nobody scored in the 40s, one person scored in the 50s, 6 people scored in the 60s, 8 people in the 70s, 7 people in the 80s, and 5 people in the 90s. Yeah. So it gives you a quick picture, a quick view of what that looks like. Now, all this being said, okay, GeoGebra, which we'll take a look at starting on Wednesday, it can do this really quickly and really nicely, and we could export the histogram, we could export a stem plot, we could export a box plot pretty nicely to a presentation that we're making or a paper, okay, and that's freely available statistical software. So we have some options available to us, okay, that aren't from the 1980s, okay. For spreadsheets, we'll take a look at those as well. Spreadsheets, some of the commands are a little bit obscure. They're not really intuitive if you're not used to working with spreadsheets. But spreadsheets are commonplace, right? They're everywhere. They're going to be in your future. So it's good to have a little bit of practice with those as well, okay? So I wanted to give you a quick look at the calculator today, but our focus the rest of the week, both with these statistical calculations and with creating these graphs or these displays, the focus will be with the other technology. All right, we're done with the calculator for today, so let me get out of here. And there I am again. Okay, and we're back. Now, last idea for today is standard deviation. Standard deviation is the measure of spread that goes along with the mean. And I just spent the last half hour talking about the 5-number summary, Q1, Q3, min, max. Okay, that was all about the median being the measure of center there. Now, if we're using the mean as our measure of spread, we want to go with standard deviation. Now, to calculate standard deviation by hand, not something that you will have to do, but as I said, I want to show you how it's done so you get an idea of what it represents. Okay? Now, the standard deviation and the variance are kind of two measures that go off of each other. The variance is the standard deviation squared. Now, we're not really going to be talking about variance much until we talk about our last measure of statistical significance, a test for that with an ANOVA test, an analysis of variance at the very end of the year. Okay? But really, variance is just a step on the way to standard deviation. Okay? Basically, what standard deviation is it's an average measure of how far away each data value is from the mean. Okay? So look at this equation for variance here. S squared, okay? S is standard deviation, so S squared is variance. X1, our first data value, minus X bar. Okay? A point minus the mean. X2 minus the mean. X3 minus the mean. All the way up through our last term, X sub n minus the mean. Okay? Now, some of these values are bigger than the mean, Some of these values are smaller than the mean. We want to turn them all positive, so we are going to square each of those differences. Yeah, you know that a negative number squared is positive. And because this is essentially the average distance away from the mean, we're going to be dividing by not n, the number of items in the set, but n minus 1. When we divide by n minus 1, this gives us sample standard deviation. Okay. Population standard deviation, it'll be dividing by just n. That's why there's that difference with the calculator. Okay? Now, it's not a big difference. There are theoretical reasons for that we're not really going to get into right now. I'll talk a little bit more about why that's n minus 1 in a couple minutes here, but we could condense this equation down into sigma notation, every point minus the mean squared, add up all of those squared differences, and divide by n minus 1 to get from the variance to the standard deviation. You're then taking the square root of that. Remember, you had squared everything, so now you take the square root. That is the standard deviation. Okay? The big thing to remember about standard deviation, it is, in essence, an average measure of how much the data values differ from the mean. We have a little example here of 5 students, 5 freshmen at Georgia Southern University. Their verbal SAT score in 2010, they had a mean of 548. Now this student right here scored below the mean, 490. So 490 minus 548, 58 points below the mean. This student scored a 650, above the mean. So 650 minus 548, that's 102 points above the mean. Here are all of those differences. Here are the raw scores. The mean of 548. We see 2 of them are negative. They were below the mean. 3 of them are positive. They are above the mean. So those differences squared give us these values. We add them all up to get the sum. So the sum is 24,880. We are dividing by n minus 1. Now, there were 5 items in this set. So we're dividing by 4. Basically, that n minus 1 is called degrees of freedom. Essentially, what that means is if you are one of those data points, how many alternative points do you have? Okay? 1 less if you take yourself out of the mix. Okay, so n minus 1 is the typical way to get this number of degrees of freedom. Okay, we'll expand on that definition as the year goes on. So that 6220 is the variance. Take the square root of that. We have about 78.87 as the standard deviation, the sample standard deviation for that small data set right there. That's what I was saying. N minus 1 is called the degrees of freedom. Sample standard deviation measures the variability about the mean and should be used only when the mean is chosen as the measure of center. It doesn't really make any sense for us to be working with median and use a standard deviation. Okay? Standard deviation is calculated from the mean. Okay? You're speaking a different language, a different measure of center if you're bringing in the median. Okay? Because of the way it's calculated, the standard deviation cannot be negative. Remember, that last step is taking the square root. So we could not have a negative standard deviation. It doesn't make sense. It's a distance. It's a distance of how far it is from the mean. It is possible to have a standard deviation of 0. Flash back to that first warm-up problem that we had. On average, people are losing 10 pounds with this piece of exercise equipment. Well, if you had that sample size of 5, and each of those 5 people lost 10 pounds, there is no variation to that data set. So there is a standard deviation of 0 if everybody's getting the same exact value. As the observations become more variable about their mean, the standard deviation gets larger. meaning that if there's a greater range, a greater spread, the standard deviation is going to be bigger. Standard deviation does have the same units as the mean. So if the mean is measured in pounds, standard deviation will be measured in pounds as well. Okay, kilograms and kilograms. Like the mean x bar, S is not resistant. A few outliers can make the standard deviation very large. If we have that $40 million mansion, okay, serving as an outlier, well, we have a lot more spread in our data set now. Okay, all these $200,000 homes and then a $40 million mansion. Not only is the mean going to be much bigger, the standard deviation is going to be much bigger because we got to get all the way up to that mansion, that outlier that's included in our data set now. So it says we now have a choice between two descriptions for center and spread, mean and standard deviation, median and interquartile range. Okay? You want to pick one based off of your data set. Okay? It says the 5-number summary is usually better than the mean and standard deviation for describing a skewed distribution or a distribution with strong outliers. Okay? Use X bar and the standard deviation only for reasonably symmetric distributions that are free of outliers. Outliers mess up the mean. So if you have a data set that is skewed or has possible outliers in it, you're probably going to want to use median and the 5-number summary. If you have a data set that's pretty normal, and by normal I don't mean like every day, I mean it fits a normal distribution, okay? It fits that bell curve pretty well, it's pretty symmetric, then mean and standard deviation are the way to go. We'll practice with this. We'll get more familiar with choosing the appropriate measure of center. All right, the very last thing that I have for today. This is something that the book kind of throws in here. It's kind of like overall guidance for solving a statistical problem. Okay? Kind of stands away from the rest of what we talked about in this section. In stats, like, every problem that we do is a real-world problem, okay? Long gone are the days of algebra where Timmy has 10 apples and Johnny has 7 apples, and together, how many apples do they have? No. Okay? We've looked at real-world data sets. Okay? We're going to be looking at more. We're going to be finding our own. We're going to be compiling our own data sets. So rather than just like work with artificial numbers or fake numbers, once we perform the calculation, we still have the important step of drawing conclusions and making inferences about, well, what does that number mean in the context of this problem? Okay, that's just as important as doing the equation itself. So they analyze it based off of these 4 steps. Okay? First one, state the problem. What is the practical question in the context of the real world setting? Okay? What are you trying to find here? Okay? Be thinking about what that is, not just a procedural algebra 2 kind of an approach where I have to do 30 of these problems. Okay? If I ever assigned you 30 problems, your hand would fall off. Okay? No, you've seen from the homework assignments that you've done and the one that I have assigned for you for our next one, like, it's whatever, it's 10 problems, something in that neighborhood, okay? Some of them are short, some of them are a little bit more detailed. Those more detailed ones, I don't give you as many because they take time. I want you to think about everything. Make a plan. What specific statistical operations does this problem call for? Okay? Using the hints that are given in the problem, how am I going to solve this? Make graphs. Carry out any calculations that are needed for that problem. Okay, that's the solving. Okay, this might be what you have been doing, okay, without thinking about the rest of this. And lastly, conclusions. Okay? Once you run that equation and you have your answer, you made that graph, what is it telling you? What inferences can you make? Okay, give your practical conclusion in the setting of the real world problem. Okay, so bring it back to the context that you started with. keep this process in mind as you start our homework assignment, okay? Your next homework assignment is listed on Canvas. It's on our agenda. It's on your Canvas calendar for Chapter 2. It will be due Thursday morning by the end of homeroom, okay? So you have a little bit of time with that. I will see you next on Wednesday. As I mentioned, on Wednesday for our remote learning, our 25 or 30 minutes together, I'm going to start to walk you through using spreadsheets and using GeoGebra to analyze data sets, okay? It's a little bit easier. We can compare larger data sets a lot easier when we get away from that calculator, okay? Friday, we'll be using that time to work on like a little project assignment that you'll be getting on Wednesday, okay? So, I did a lot of talking today. I don't want you to get the idea that like every class is going to be me up here on my soapbox for an hour plus just like talking about statistics and stuff like that, okay? It took me a little bit of time to figure out how this hybrid is working, and I think I'm getting a feel for what's working. But I want us to be able to do more with this now. We have the basics underneath us. Okay? Now we can start to kind of use it and solve problems a little bit better. Okay? Anybody have any questions right now? You're here, you're at home. All right, so we do have a homework assignment for Thursday, and next time I see you will be Wednesday. All right, so we have about 7 minutes or so that you can get started on that assignment. People at home, you're free to sign off, okay? Have a good one. I'll see you.